Okay, welcome to Unit 2, where we talk all about bonding and the nature of solids and compounds. So we're going to jump in and talk about our three main types of bonding. Okay, so we're first going to talk about chemical bonds. We're going to talk about why they form, what determines what type of bond forms, and we're also going to talk about bond strength. So let's first talk about our three basic types of bonds. So our first type of bond is an ionic bond. Ionic bonds are formed by electrostatic attraction between oppositely charged ions. So we have to have ions first. So that means that electrons have to be transferred from one atom to another in order to form ions. And then the attraction between the two is based on the attraction of two oppositely charged ions. Our second type of chemical bond is the covalent chemical bond. This forms molecules, and in covalent chemical bonds, these are based on the attraction of the electrons of one atom for the nucleus of another atom. And so this is what we typically talk about as sharing of electrons. This means that the orbitals of the atoms are overlapping and the electrons are in the orbitals of both atoms. And finally, we have metallic bonds. These are where multiple atoms share all of their electrons across all of the atoms. And we typically call this the sea of electrons. And the type of bonding very much influences the characteristics of the compounds. So let's talk about covalent bonding first. So when we talk about covalent bonding, it's really a balancing of repulsive forces and attractive forces. So first we have the repulsive forces of the electrons of one atom for the electrons of the other atom. And we have the repulsive forces of the protons of one atom for the protons of another atom. But then we have an attractive force, and that's the attraction between the electrons of one atom and the protons of another. And so covalent bonds are really all about balancing these opposing forces. And so as two atoms approach one another, we start to see the attraction of the electrons of one for the protons of the other, but we also start to see repulsion of the electrons of one for the electrons of the other and protons of one for the protons of the other. And the point at which the attractive and repulsive forces are most finely balanced is where a bond forms. And so that balance between attractive force and repulsive force is really what determines the length of the bond. So you'll notice in our illustration here of our two hydrogen atoms, as they get closer together, then this attractive force starts to pull them together. And as they reach this optimal distance from one another that maximizes the attractive forces and minimizes the repulsive forces, we form a bond, and that's the bond length. So the lowest potential energy point is where the bond forms. If multiple bonds form, so if you have a double bond or a triple bond, that tends to shorten this bond length and also strengthen this bond. So if we think about all of this as a balance and as a relationship of potential energy, you can see that this explains why helium and many other atoms aren't diatomic. Because as we go from two separate helium atoms and we bring them closer together, then you start to have more and more repulsive forces. It takes ever more energy. And so this bond is never going to form because this bond would require energy, but forming bonds always releases energy. So when we talk about covalent bonds, we have two different types of covalent bonds. This is really along a spectrum. Okay, we have non-polar covalent bonds where electrons are shared equally and there's no positive or negative end. And we have polar covalent bonds where electrons are not shared equally and we have a partially positive and a partially negative end of our bond. So how do we determine whether it's going to be polar covalent or non-polar covalent? That all comes down to electronegativity, which is abbreviated with the chi. So electronegativity is a measure of the ability of an atom in a molecule to attract electrons to itself. And we know the trend in electronegativity, and we've been talking about electronegativity for a year now. Electronegativity was proposed by Linus Pauling. Linus Pauling received a Nobel Prize in Chemistry for his work on bonding and a Nobel Peace Prize. He's one of the only people to ever receive 2 individual Nobel Prizes. So when we talk about bond polarity, we are talking about a bond where the electrons are shared unequally. Because the electrons are shared unequally, we talk about having a higher electron density at one end and a lower electron density at the other end. And this results in a partial positive charge on one end, the end with the lower electronegativity, and a partial negative charge on the other end, the end with the higher electronegativity. And we use this symbol, this lowercase delta, to represent partial. So this is a partial positive charge on hydrogen and a partial negative charge on chlorine. Now, you're not going to be expected to know electronegativity values, but you do need to know the trends in electronegativity. And the farther apart 2 elements are on the periodic table, the more likely it is that they are going to have different electronegativity values. So chlorine has the greater share of the bonding electrons than hydrogen does. So chlorine is going to have a slight negative charge, and hydrogen is going to have a slight positive charge. Now, one of the interesting things about polar bonds is that they are actually stronger than nonpolar covalent bonds. If we were just going to predict this, the amount of energy that was released when this bond formed, we would predict based on Coulombs Law, 339 kilojoules per mole. But in fact, this bond releases 432 kilojoules per mole. So that difference is proportional to that difference in electronegativity. So the bigger the difference in electronegativity, the more polar the bond. And the more polar the bond, the stronger the bond. Which brings us to ionic compounds, and we'll come back to that thought. So these are just different ways of looking at these polar covalent bonds. We can see that when 2 fluorine molecules bond, they bond in a non-polar fashion because they're going to share the electrons equally. But when hydrogen and fluorine form a covalent bond, hydrogen is much less electronegative than fluorine, and so we have a much higher electron density here on the fluorine end. Fluorine is going to pull harder on those electrons, and therefore it is going to have a higher electron density and a partial negative charge. We could also look at these this way. In A here, we have 2 atoms sharing electrons equally. In part B, we see this probability map. We see that the right-hand end has a partial negative charge, and it has a higher electron density. And if we look at part C, this is when we actually have an ionic compound. So in this case, the electronegativity difference is great enough that the electron has been pulled completely away from the atom on the left and is residing with the atom on the right. And so we have a positive ion, a cation, and a negative ion, an anion. So how do we determine this character of the bond? If we actually know the electronegativity values, we can simply subtract the electronegativity value of one atom from the electronegativity value of the other atom. We generally say that if the difference is less than 1.7, it's covalent. If it's more than 1.7, it's ionic. Different textbooks will use different values for this, so this is not an absolute determiner of the character of the bond. But I want you guys to think of this really as a spectrum, from completely nonpolar covalent at one end to completely ionic at the other, and everything else falls somewhere in between. So the ones down here have more ionic character, the ones down here have very little ionic character, and here in the middle we have our polar covalent molecules, which have some ionic character. So if we were going to classify the bonding between chlorine and calcium, that electronegativity difference is 2. and so we would classify that as an ionic bond. The difference between chlorine and oxygen is 0.5, so we would classify that as a polar covalent bond. And technically, the bond between chlorine and bromine with a difference of only 0.2, we could classify as non-polar covalent. It does have some polar characteristics, but very, very little. So if we look at these, we'll notice that down here we have low electronegativity differences. These are covalent compounds. Some of them are nonpolar covalent compounds, and some of them are polar covalent compounds. Up here we have our ionic compounds. And so we talk about percent ionic character. Now, hydrogen fluoride or hydrofluoric acid, you'll notice is up here at almost 50% ionic character. It is certainly a covalent compound, but it has some very strong polar characteristics. So an ionic bond is mostly ionic in character. We say greater than 50%. A covalent bond is principally covalent in character, meaning that it shares. Okay, let's get back to this idea about strength of bonds. So when it comes to an ionic compound, we can really predict the strength of an ionic bond very easily by looking at Coulombs Law. And you'll remember Coulombs Law because we used it in learning how to predict the attraction of the electron for the nucleus, and that had to do with effective nuclear charge and distance. So Coulomb's law says that the energy of interaction or the strength of attraction between a pair of ions is proportional to the product of their charges divided by the distance between their centers. So you'll notice here that we have energy and not force, okay? And that's why it's divided by R and not R squared. This is also a very slightly different constant than for the force. But the idea is still the same. The larger the charges are, the greater that energy is going to be. The smaller the radius is, the greater that energy is going to be. So this means that larger ions with smaller charges are going to be attracted to one another less strongly, and small ions with large charges are going to be attracted to each other more strongly. Okay, let's do a couple of practice problems. So if we think about the bond in the molecular compound hydrogen fluoride, which of these is likely to be true? Is there a partial negative charge on the hydrogen atom? Well, we know that fluorine is more electronegative than hydrogen, so it's going to be the one with the partial negative charge. Are the electrons shared equally between the hydrogen and fluoride atoms? Definitely not. Fluorine is the most electronegative element on the periodic table. It does not share equally with anything except itself. The bond is extremely weak. Well, we said the more polar the bond, the stronger it is, so we know that's not the case. So we have to go with this bond is highly polar. All right, our two pure elements react to form a compound. One is an alkali metal and the other is a halogen. Which claim can we make about this compound? It has the formula Xz2. Well, we know if it's an alkali metal, it's going to form a +1 ion. And if it's a halogen, it's going to form a -1 ion. So these should be in a 1-to-1 relationship, so that would not be Xz2. It does not dissolve in water. Well, we don't know. Most halogen salts and most alkali metal salts, well, all alkali metal salts dissolve. So we know it does dissolve. It contains ionic bonds. That's very likely. Even though we don't know electronegativity values, we know that these two things are on opposite sides of the periodic table, so they're going to have very big differences in their electronegativity values. So it is going to contain ionic bonds. These two elements, carbon and selenium, have the same electronegativity value. Which of the following claims is likely to be true? The carbon to selenium bond is unstable? Well, probably not. That would be carbon bonds pretty stably with most anything. The carbon to selenium bond is non-polar covalent. Well, with the exact same electronegativity value, that is going to be true. If we look at the others, the compound has the empirical formula CSE. We don't necessarily have enough information in order to answer that question, but if we just look at where selenium is on the periodic table, it's not going to bond. It's not only going to form one bond with carbon. And a molecule of the compound will have a partial negative charge on the carbon atom. No, it's going to have this zero charge on both atoms. All right, which of these graphs correctly shows the relationship between potential energy and internuclear separation for two hydrogen atoms? Well, we saw this graph earlier, and we know this would say that as they get closer together, that potential energy increases. We know that's not the case, so it can't be A or B. So we're down to C or D, and you hopefully will remember that as these two get closer together, their potential energy decreases. At this point, at the bottom of the curve is where the bond forms. This is the lowest possible potential energy, and this is the length of the bond. So it's C. Okay, so quick review of bonding. Hopefully that's all coming back to you. And if you have any questions, as always, just let me know.